Hello. So as previously mentioned, I talked about the specific ways that you can manipulate the wave function and certain properties and features of it, such as the probability density. Normalizing the wave function is quite important, as well as trying to find position, momentum, and energy operators, or expectation values using their respective operators. Using the probability density and the wave function to find those and extrapolate that information. But for this video, I just wanted to go ahead and talk briefly about a practical example of trying to find the probability density of a particle with a certain wave function from certain restrained values of position, as well as trying to find the normalization constant for a wave function, the same one. So let's say there is a ball and it is constrained to move along a line inside a tube of length L. So we're going to draw this line. So that's the X. That's going to be the position axis. And this is going to be the wave function. The wave function is going to be on the y-axis to observe in essence, as the position changes, how the wave function varies. So basically what the shape of it looks like. So we're going to go from here to here. So it's going to be about an even split. And this is going to be negative L over 2, and this is going to be L over 2. So again, we have this ball, and it's moving along a line inside of a tube that is of length L, right? And so we can easily see that the length from negative L over 2 to L over 2 is about L. And so the question is, say that this is his wave function, right? And it looks about like a cosine function. It's a simple cosine function. What is the probability of finding the ball, if it's in this tube of length L, in the last 1/4 of the tube, right? So we can picture from here to here is the first half, and then from here to here is the second half. But if we divide this into quarters, we have this is the last quarter of it. So we have it from about L over 4 to L over 2. But let's look at it differently. Okay, so the wave function can be written, right, as a cosine, because it's a cosine function, times kx, where k is 2 pi over wavelength. It's this wave number. But we don't know what a is. Right? A is the normalization constant that we need in order to figure out and fully write out and know what the cosine function is that we're describing with this graph. But we don't know what that is, right? But all we know is that this is the wave function that we saw in this graph from the values where position is from negative L over 2 to positive L over 2, right? So let's look at it, right? So beyond this interval, but beyond the interval L over 2 to 0, right? There's no probability that the wave function is going to be there because it's only represented with this cosine graph. So evaluating the wave function at x equals L over 2 is going to help us find the normalization constant. So let's see. At x equals L over 2, a of cosine, so again, the wave function that we're writing, of KL over 2 equals 0. And eventually, we find that the normalization constant, whenever setting this to 0, is going to be equal to the square root of 2 over L. Now, this normalization constant right here is vital to understanding what type of function that we're dealing with. Because until we measured that this normalization constant was what it was, because we used the different values of basically the different boundaries, right? So to determine what this wave function would look like for this particle, say like an electron, we need to figure out what the constant is, the scalar value that is multiplied by this cosine function, to see what the function really is shaped like, right? And what the wave function matches like for this particle at this, between these periods of time, because they can vary. So we measured it. Now we know that we can rewrite, sorry, I forgot that up here. That's cosine, or the psi, which represents the wave function. So psi, we're going to denote again, is going to be, now because we know the a value, it's going to be square root of 2 over L, right, that a constant, multiplied by cosine of pi x, pi x over L. Because remember, we have the k equals the 2 pi over the wavelength, and then we end up trying to substitute that value, and we derive this pi x over L inside the parentheses here. And pi x over L, and this is true for, remember, minus and positive, L over 2. So this is what we know is our wave function, right, from these position values. So what we can do with this is, as we mentioned, we can find the probability density, right? So the probability density is, what is the probability, like tying back to the question again, that we can find the ball that's traveling in this tube of length L, right, because this is length L, between the L over 4 and L over 2, right? So the last quarter would be from these two values. So what's the probability we can find that this, in this area, basically? Well, the formula for probability density for this example, and it's related to what we talked about earlier. So the probability from x equals that fourth of L to L over 2, just like we said here, the shaded value, is going to be equal to the integral from L over 4 to L over 2, right? The sum of all possible states from the x value of L over 4 to L over 2. So the integral, the sum of all possible wave function values, and we're going to just substitute in this 2 over L because it's just the wave function written. And then again, cosine of this pi x over L. And we're going to square this. It's going to be absolute value squared with respect to x. And so what this is going to tell us is the sum of all possible probabilities that is going to represent how likely the particle is going to be found from these x values, given this wave function that we found after we normalized it, right? So it's going to be able to give us a real number. So now that we can obtain some type of real sensible idea about how likely, reasonably likely, since quantum mechanics is so probabilistic, right? It's never definite because we're using the statistical interpretation. We calculate this to be about 0.091, right? And we talked about it being 1. So the all probabilities from it to be from negative L over 2 to positive L over 2, if the ball is traveling in this length, or this tube of length L, then we know from it to be, the probability density from negative L over 2 to positive L over 2 of finding this ball in there is 100%, because it's traveling in that tube. But now we've found what the probability density, or how likely it is for it to be found in the last quarter of the tube. And since we just now found that it's 0.091 relative to 1, representing 100%, we can safely say that that is it's equal to 9.1%. So relative to being, or compared to being 100% likely to be found in this entire tube, which makes sense, in the last quarter of the tube, it would be 9.1% likely to find it. And so that right there really, it says a lot, right? Because you know probability, or probability-wise, that's how likely you're going to find the ball in the last quarter of the tube, given that its length is represented in a constant, right? And we have this function, we normalized it so we can obtain a real sensible value of what the probability is. And it's important that we normalize this wave function, because if we don't normalize it, it's all possible states. And we don't have this a value. and if we don't have this a value, we're dealing with another constant when we're trying to integrate this, and we simply can't solve it. So in order to find that value, we used what information we know, right? So from negative L over 2 to positive L over 2, we know 1 has to be equal, all of the possible values for the probability density to be found in between these values has to be equal to 100% or 1. And we ended up basically, and I didn't write this out, but I mean, I can just write this out very briefly. We know that the probability, we're going to just relate this right here, from x equals negative L over 2 to positive L over 2, since it's in this tube L and it's not outside of it, has to be equal to, let's see, so it's this right here, so it's going to be negative L over 2, change the limits of integration, multiplied by, instead, remember, we don't have this a value yet, so that we would have written it as a cosine of pi x over L squared dx. It's getting a little sloppy here. It's actually this one. So if we had this, we would know that it would just be negative L over 2, right, to positive L over 2. And we would end up having this a squared cosine squared pi x over L, but we wouldn't really know what to do with it. But we know that the probability or the likelihood that we're going to find it in between this constrained position interval is going to be equal to 100%, or 1, right, relative to, or compared to this 0.091. So what we do, or what we did, would be we would take this a squared out, and we would just say a squared, because it's a constant, is equal to, and then the integral of blah de blah, which is, you would just solve the interval. And that's how we ended up finding that this a squared, because we would have to take the square root of it, and that's why we got this square root in here, and that's how we got this square root of 2 over L. And so it's important that we find that a, so that we know that we have the full and fully accurate and descripting wave function that we can use to find the probability density of finding it in that last quarter of the tube. And so that's really why we did that, and why doing that is so significant. It gives us a very sensible and accurate probability on a scale that we can understand and that actually makes sense. Doing computations with information that is known to us given the context of the problem. So thank you. I hope that helped you, and awesome.